Section 18.6, the electric field. Now, before we get into what the electric field is, let's first imagine a scenario where we have a bunch of charged objects, right? So we have this rod that has negative charges, maybe from rubbing on the fur. There are these other two metal spheres that each have their own charges, right? One of them's negatively charged, the other one's positively charged. Cool. Now, in the midst of this environment of having a bunch of different charges, we are going to add a positive charge Q naught. So we're going to put it in the mix and say, hey, what kind of force would that experience? And it would experience a force that's the vector sum of the forces from all the other charges, right? This is a continuation of the last section where we saw that the force on a charge is going to be a vector sum, right? So Q naught, because it's positive, which we could even draw in a little positive here to help us remember that, would feel attracted to the rod, but also feel attracted to this ball on the right, but it would feel repelled from the positive ball. And so the sum of all of those would come out to the net force pointing somewhere up and to the right. Now, this Q0 is a random charge, but we're going to instead make it more general and call it a test charge. So a test charge is going to be a general term, and it's going to be something that allows us to test the environment so that we could say, hey, if we put a small positive charge here, what kind of force would it experience? So the key is that we want the test charge to have a pretty small magnitude so it doesn't influence the other charges. We're also always going to assume that the test charge is positive. So that's something else that you can note and remember. It's a useful little bit to hang on to. So we're going to pay attention to what a positive charge does. Now, thinking about this specific example, we can start to put some numbers to it. So look at an example of a test charge. So the positive test charge has a magnitude of 3 times 10 to the minus 8 coulombs and experiences a force of 6 times 10 to the minus 8 newtons. Now we want to find the force per coulomb that the test charge experiences and then predict the force that a charge of 12 times 10 to the negative 8 coulombs would experience if it replaced the test charge. Now we don't know the values of how much charge these other objects have. I can tell you from experience, it's a lot more than 3 times 10 to the minus 8 coulombs. That's a really small charge, which is what we said we wanted for a test charge. And just as I mentioned, it will always be positive as a test charge. All right, now if we want to find the force per coulomb, let's think for a moment about what force per coulomb is. Force per coulomb, that's going to describe the amount of force divided by the coulomb, that's the charge, right? So the total amount of force divided by the amount of charge. And we know the force, and we know the charge. So we're in good shape to be able to solve part A. Now what about part B, where it says to predict the force the charge of 12 times 10 to the negative 8 coulombs would experience if it replaced the test charge? Well, one option here, if you are comfortable working with numbers, is we could say, hey, this charge in part B is 4 times bigger than the previous test charge. So I expect the force should be 4 times bigger. But if you aren't comfortable with that jump, because it is a little bit of a jump, we can use our result from part A, right? Because notice in part A, we got the force per charge, but then we can multiply by our new charge, Q2, to get the force that Q2 would experience. So that's a pretty nifty workaround. Let's see how it works out in the math. All right, so in A, we have the force divided by that original charge, Q naught. So 6 divided by 3, the 10 to the minus 8 to cancel, and we're left with 2.0 newtons per coulomb. And that number can then be used in part B to find the force, where we can use that 2.0 newtons per coulomb and multiply it by the amount of charge present. It's just rearranging this to get the force then that this larger charge would experience. And sure enough, look, 24 compared to 6, that is 4 times bigger. So that matched exactly what we expected. Now this force divided by charge seems a little strange, but it is also really useful. And this, it turns out, is our definition of the electric field. So we came about it from a roundabout way, but this brings us to the electric field. That the electric field that exists at any given point is the electrostatic force experienced by a small positive test charge placed at that point divided by the charge itself. So we now have that equation that we used in the last example is a formal equation that you could write on your crib sheet. It's a good one to highlight. The electric field is equal to the force divided by the test charge. Now our SI units of the electric field are indeed what we got in part A, that newtons per coulomb, force per charge. So that's something you will want to keep track of. This equation is one that we will also down the road rearrange to write as the force is equal to the amount of charge times the electric field. So that's a handy thing too. If you happen to know the electric field first and the charge present, you can figure out how much force there is. One other thing to note here is that in both of these equations, there are vectors over the force and the electric field, because both of these are vectors that have a direction. And they usually point in the same direction, assuming that you're dealing with a positive charge. So let's take a look at that. All right, so we have the electric field right here. There's a positive 18 times 10 to the negative 8 coulombs. And notice here, it's a negative charge, negative 24 times 10 to the minus 8 coulombs. But in both cases, the electric field is pointing up and to the right. Why is it pointing up and to the right in both cases? The key is that the electric field is created by the surrounding charges. And so that electric field will always point in the direction as though there was a positive charge there. But you might have put a negative charge there. The electric field will be in the same direction. So that's an important distinction and it can help our understanding of the electric field, that it's trying to describe the environment that a charge would experience, everything else around it. Let's look at another example that's closely tied to this. Example 7, an electric field leads to a force. The charges on the two metal spheres and the ebonite rod create an electric field at the spot indicated. The field has a magnitude of 2.0 newtons per coulomb, which is what we found in the last example. Same numbers here. Determine the force on the charges in A and in B. All right, well, if we know this electric field magnitude, then we can figure out the forces. How so? Well, we can use that definition of the electric field, rearrange it to solve for force, right? That the force is equal to the amount of charge times the electric field with the vector symbols. And note, this is not absolute value, so the sign does matter in this equation. Let's take a look. All right. So here they do it with absolute value. I don't prefer that, but it is a way to get the magnitude. So you have the force times the amount of charge times the electric field. So in part A, it's that electric field of 2 newtons per coulomb times the amount of charge, 18 times 10 to the negative 8 coulombs. So that comes out to 36 times 10 to the negative 8 newtons. If you include the charge, there would just be a positive there, and this would come out positive. Now, in part B, it's a negative charge. So if you actually included that negative sign when you put in that result, your force would come out with a negative sign as well. I prefer this because then that tells you the force is in the opposite direction as the electric field. In case A, because it's a positive charge, the force points in the same direction as the electric field. They're just working together. But in part B, because we now have a negative charge, it will need to be a force that is opposite. Because remember, the electric field tells you about what a positive charge would experience. It's the opposite of a negative. All right. So I think this is a good point to pause, but there is so much more to come on the electric field. We'll get specific to instead of a bunch of different things contributing to it, the next video will take a look at the electric field due to a point charge. So stick around, you're going to want to see it.